A binomial series is a Maclaurin series expansion of functions like this ones here. Now, it's used for fractional and negative powers. Um, so I'm going to work out this question, and then through the process, you should be able to get the intuition of this idea. Now, find the Maclaurin series for f of x is equals to 1 plus x to the power k, where k is any real number, and find the associated interval of convergence and radius of convergence. So we follow the same process that we used to in the beginning to find Maclaurin series for any function, which means you have to find the derivatives and find the value of those derivatives at x is equals to 0. So f of x is equal to 1 plus x to the power k, and f0 will be equal to 1. Now f dash x, first derivative, will be k into 1 plus x to the power k minus 1, and f dash 0 will be equal to k. The second derivative of this function will be k into k minus 1, 1 plus x to the power k minus 2, and the value of the second derivative at x is equals to 0 will be k into k minus 1. The third derivative will be k into k minus 1, k minus 2, and then 1 plus x to the power k minus 3, and the value of the third derivative at x is equals to 0 will be equal to k into k minus 1 and k minus 2. Okay, just want to organize this information so that somewhere there. All right, let's carry on. The fourth derivative will be equal to k into k minus 1, k minus 2, k minus 3, and then we have x 1 plus x to the power k minus 4, and the value of the fourth derivative at x is equals to 0 will be k into k minus 1, k minus 2, and k minus 3. Okay, so we can definitely, because of space, we can't continue going on, but we can clearly see the connection here. Now, suppose I want to find the nth derivative. First of all, if you look at, let's start from the first derivative. We stopped at, so from the first derivative, where did we stop? At 0. Okay, I need to highlight this. First derivative, we stopped at 0. You can see that clearly. Second derivative, we stopped at 1. Third derivative, we stopped at 2. Fourth derivative, we stopped at 3, which means, and it's actually clear here, right? You can see that connection. So which means that for the nth derivative will stop at, so for the nth derivative, we'll end up with k into k minus 1, k minus 2, whatever comes next, up to, there's a point that you're going to stop here, all right, which will be k minus n minus 1. Because here when n was 4, we stopped at 3, which is 4 minus 1. When n was 3, we stopped at 2, which is 3 minus 1. When n is equals to n, then we stop at k minus n minus 1. All right, so this is where we stop. This is where we stop. And of course, we have multiplied by 1 plus x to power k minus n. Because if you look at the powers, they're less by 1 again. If you look at that power, k minus 1, k minus 2, k minus 3, k minus 4, and therefore k minus n. All right? And here are the powers of where we are going to stop. So that is n minus 1. So this is basically where you stop. I need to write it here. This is where you stop. Okay, so that is the pattern of derivatives and the coefficients. So what you're going to do is now we can use, we can find the Maclaurin series of basically this function, and you can use the formula that we established initially. Now, using the formula that we established initially, use the formula. So initially, when I introduced the Taylor series, remember Maclaurin series is Taylor series centered at 0. So when I introduced the Taylor and Maclaurin series, we derived this formula here, where we said that f of x is equal to the sum from n. So this is basically Maclaurin series expansion, fn 0 x to power n over n factorial. All right, you remember that when we introduced the Maclaurin-Taylor series. If not, you can watch the videos on my channel, the one that explains that. Anyway, so now what we have here is we have this function. We have the nth derivative of this function. Now, what you can do is we need this bit. We need this bit to plug into the formula. We need that bit there. And I can actually find that from the nth derivative. So I just need to find the nth derivative at x is equals to 0. So basically, what I mean is the nth derivative of this function at x is equals to 0 will be equal to k into k minus 1. I don't have to write all this. Up to where I'm going to stop, which is k minus n plus 1. You can just write it as k minus n plus 1. All right. So this bit is what I am going to plug into this formula. So this is what I'm going to plug there. Okay, so what I'll end up with is f of x. Basically, f of x will be equal to the sum from n is equals to 0. Now remember, f of x is actually, I think it's better if I just write what it is. 1 plus x to the power k, way up here. That's what you're trying to, we're trying to find the Maclaurin series expansion for this function. So that will be equal to the sum from n is equals to 0 to infinity of, so in place of the nth derivative of this function at x is equals to 0, I'll just plug in this guy, which is k into k minus 1 plus whatever comes next up to where I'm going to stop, which is k minus n plus 1 over n factorial, x to the power n. Okay? All right. So basically, that's what you end up with. And need to take this off. What I'm going to do next is to just write an expansion for this series. But one thing that you need to know is that f0 is actually equal to 1. All right? f0 is equal to 1 here. Very important. f0 is equals to 1. So which means basically the first term, remember f0 is the first term. If you check your Maclaurin series expansion, all right, this is the first term, which is f0, and our f0 will be 1. So back to my expansion here, I'll end up with this. So this will be equal to, if I just write the expansion, that will be equal to, so I can write here 1 plus x to the power k. I may need more space, right? So 1 plus x to the power k will be equal to 1 plus kx plus k into k minus 1 over 2 factorial x squared plus k into k minus 1 k minus 2 over 3 factorial plus whatever comes next. Now, this is when n is equals to 0. Now, we've just said that the first term is 1. Okay? The first term is 1. So, which means that here, remember the Maclaurin series expansion, this is when n is equals to 0, n is equals to 1, n is equals to 2. So when n is equals to 0, what you're basically finding is f0, which happens to be 1 in our case here. So that is 1, but now when n is equals to 1 here, when n is equals to 1, then that means that in our formula, we are going to stop at this point. So when n is equals to 1, you're going to stop at k. And that's why I stopped at k here, when n is equals to 1. When n is equals to 2, it means in this formula, oops, it means in this formula, you're going to stop at 2. Now, negative 2 plus 1 will be negative 1. So you're going to stop at k minus 1. When n is equals to 3, then what you're going to do is you're going to stop at -3 plus 1, which happens to be -2. So you stop at -2 here. All right. So that is basically the Maclaurin series expansion for this function. So we have finished the first part of this question, which is finding the Maclaurin series expansion for this function. That is what we have here at the bottom there. And now I'm going to move to the second bit where we are required to find the associated interval of convergence and radius of convergence. So to find the interval of convergence, we are going to use the ratio test. So next step, use ratio test to find the interval of convergence. Okay, so what you're going to do is, you remember the ratio test. So if a series converges, then the limit of the absolute value of S sub n plus 1 over S sub n should be less than 1 as n approaches infinity. So we are saying that if the limit as n approaches infinity of S sub n plus 1 over S sub n is less than 1, then the series converges. Okay, so what we need to do is we need to find S sub n plus 1 and S sub n. Now, here again, S sub n will be equal to, because this is the series representing this function. So basically, S sub n, we can write S sub n. S sub n can be found from here, all right? This bit here. This will be, let me just take off that 3. Okay, so this bit here will be our S sub n, all right? That will be our S sub n. So my S sub n will be k into k minus 1 up to where I stop, which is k minus n plus 1 over n factorial. Now, S sub n plus 1, S sub n plus 1 will be k into k minus 1 up to k minus, in place of n, I plug in n plus 1, plus 1. And up here, let me just check S sub, oh, I forgot x to power n. All right, so here we have x to power n. So, which means at this point, I'm going to have x to power n plus 1, all this over n plus 1 factorial. Okay, so I have S sub n, I have S sub n plus 1, and now my plan is to plug these guys here and find the limit of this as n approaches infinity, form that inequality, and find the values of x for which this series converges. All right, so let's carry on. So I can simplify this further. So this can be given as k into k minus 1 up to k. That will just be k minus n, because this will be just k minus n, if that makes sense. And then x to power n plus 1 over n plus 1 factorial. All right. Good. So now that we have that, so we have these two guys that we are going to use, that and that, to plug into that formula. So what we'll end up with is this. We'll end up with this expression. The limit, we need space for this. So the limit as n approaches infinity of the absolute value of s sub n, which is k into k minus 1 up to k minus n, x to power n plus 1 over n plus 1 factorial, divide by s sub n, which I have at the top there, which is k into k minus 1 up to k minus n plus 1 over n factorial x to power n. Okay, so that's what I have up here. So s sub n, there it is. All right, and you can see, so s sub n, we have it there, and you're dividing these guys. All right, let's carry on to simplify this. So what I'll end up with is the limit as n approaches infinity of the absolute value of k into k minus 1 up to k minus n, x to power n plus 1 over n plus 1 factorial. Now I'm going to change this to a multiplication. So I'll have n factorial over k into k minus 1 up to k minus n plus 1 x to power n. Absolute value of that. Okay, it's a lot of things to write here, so I have to keep on checking that I haven't made any mistake. All right, let's carry on. So this will be equal to the limit as n approaches infinity of, now I'm going to break up these things. So this and that, I'll find a way of putting them together. All right, this bit and that bit, I'm going to find a way of putting them together, and this bit and that bit, I'm going to try and find of putting them together. So what I'll end up with is k into k minus 1 up to k minus n over k into k minus 1 up to k minus n plus 1 multiplied by n factorial over n plus 1 factorial. Now n plus 1 factorial, I can actually simplify. Or anyway, let me just write it because I don't want to start mixing steps here. All right, and then multiplied by x to power n plus 1 over x to power n, one step at a time. All right, next, the limit as n approaches infinity of, now before you get to k minus n, you have to go through k minus n plus 1 before you get to k minus n. So basically what I'm saying here is this numerator here, I can write it as k into k minus 1 up to k minus n plus 1 multiplied by k minus n. All right, if that makes sense. All right, before, because k minus n plus 1 is before you get to k minus n. All right, so that is before you get to k minus n over k into k minus 1 up to k minus n plus 1 multiplied by n factorial over n plus 1 multiplied by n factorial. In this case here, you can just simplify them using indices, so that is just x. Okay, that's just x. We can carry on. So this case here will cancel. That's all gone. And that's gone as well. So you'll end up with the limit as n approaches infinity of k minus n over n plus 1 multiplied by x. This can be written as the limit as n approaches infinity of, you can actually factorize out x, so absolute value of x, and we can write this as absolute value of x, and then we can say the limit as n approaches infinity of k minus n over n plus 1, which will be equal to, this will be equal to absolute value of, and here you can use LHR, use L'Hopital's rule. So use LHR. So what you'll end up with is this will be multiplied by absolute value of -1. Okay, which is just equal to the absolute value of x. Okay, now, so now that we have that, by ratio test, the series converges if the limit, if this limit is less than 1. So by ratio test, the series converges if the limit if this limit is less than 1, not less than 0. Okay, so which means that our guy here, right, this should be less than 1 for convergence. So therefore, we can say that, so therefore, absolute value of x is less than 1 for convergence.